if you are in a part of the world where it's 2 a.m. and you can't make a session, you'll still be able to see that session on the web. Just a couple more comments on the attendance. Khalid had mentioned the really nice character of people from all over the world logging into this. I would add, after looking at the attendance list, one more thing that I think is important and relevant. If you look at the participation list, it is a rich cross-section of research-oriented folks, practitioners, as well as students. And I think that's a really important part of this workshop. And as we unfold and you see the workshop discussions, and if you've looked at the agenda, you'll know that we want to talk about the research and the technology in depth, but we also want to begin a dialogue, a very, very important dialogue in my view, of how do we transition these technologies into practice. There's sort of a lot of this technology is reserved to the domain of the research community right now. It's starting to seep into practice a little bit, but we really wanted to cover the entire domain in terms of technology, as well as embrace a dialogue of how can we begin to work these things into engineering practice. So that's a little bit of the parameter space that we set out for when we thought about setting up this workshop. So let me make a few comments that are really, I guess, motivational in scope about this workshop. And number one, engineers in performance-based earthquake engineering practice are often challenged in terms of defining ground motions that they should be designing to or analyzing to. And that is really challenged by the sparseness of the data that still persists and will continue to persist. And just to exemplify that, I'm showing a plot here of all the strong ground motion data in the peer database. And on the vertical axis of this plot, you see magnitude of earthquake. And on the horizontal axis, you see distance from the fault. Every single one of these dots is a strong ground motion record that has been measured somewhere around the world and is encompassed in this database. Well, one of the things you immediately see if you look at this is up here, where engineers may be most concerned about damaging events, very large earthquakes and in the near field, the data continues to be exceedingly sparse. And so the coverage of the data that informs empirically based methods is still really, really lacking and will continue to do so. So I think that's an important thing to keep in mind. And how do we rectify that? What are the means for rectifying that? Certainly more data, a lot more data is not going to suddenly pop up. So this issue is going to persist. Moreover, for many of the areas of high concern, we don't have any ground motion data from large events. And the example I will use that a number of you are familiar with in the US is for the Hayward Fault, here along the eastern edge of the San Francisco Bay in California. The Hayward Fault generates a major earthquake about once every 150 or so years. You can see the previous events here. The last event on this earthquake was in 1868. And obviously, that was well before the inception and the deployment of strong motion instrumentation. So although we have a significant number of small events, 3 and 4 events associated with the Hayward Fault, we can use to check and calibrate models. The point is, for many of the large events that we're concerned about and want to think about designing to in the future, we have no strong motion data for large events. So that really adds to that gap of understanding. So simulation is one really promising technique, advanced simulation, for rectifying this gap. And one can just imagine that if you had a validated, realistic simulation capability, it would really provide a transformational tool. And these are some simulations that you'll be hearing about that were recently done for the Hayward Fault. But the promise of simulation is to be able to literally generate thousands of spatially dense ground motion time histories with great site specificity. Another important thing is the ability to explore the parameter space virtually. Even when we do eventually get a major earthquake on the Hayward Fault, we measure those ground motions, that's only for one realization of rupture of that fault. So if that is, for example, a north to south rupture, it'll give us great data for a north to south rupture, but it may not give us much data for a south to north rupture, where the ground motions might be quite different. So the ability to explore and numerically the parameter space for ruptures and ground motions, it will be a really, really great thing if we can get these models validated and accepted in an appropriate time frame. And a lot of work is going on this right now. Additionally, I would say the third bullet is the ability to understand the complex interactions across the subsurface and surface interface is another really, really important feature and attribute where advanced simulation can help us and gain our understanding. You know, the engineering practice, earthquake engineering practice, has grown up, in essence, around an assumption of 1D site response. And so we often take surface motions from a point where we've measured or a point on the earth, and we apply that to the base of our structural system if we're neglecting SSI. Well, that's only really commensurate with a incident wave field that's pure vertically propagating shear and compressional waves. And that's not always the case. And so there are limitations to that assumption that we really need to explore a little more carefully. Additionally, when we do a site response calculation to account for the near surface soils, that's often done in a 1D manner. And that may or may not be valid depending on the geologic setting and the orientation of the fault and so forth. So that's something else that we really have lived with for decades, but we really need to explore. The promise of advanced simulations is for the first time we can begin to strongly couple our engineering systems with our geophysical systems and thereby understand the influence of surface waves and inclined body waves and all the things that complicate this interface that for years we've idealized. And so that's going to be another important feature of the discussions we're going to have over the next few days, is how to do that coupling and what are the implications of that. So just to drive that point home with a little bit higher fidelity, this is an example of a simulation of a magnitude 7 strike slip earthquake, where our building and soil structure model are fully coupled to the geophysics model through the domain reduction method developed by BEOLAC. And so this is really allowing us, you know, for the first time by simulating earthquake ground motions at frequencies relevant to engineering structures, to appropriately couple those domains and understand the effects of incident surface waves, inclined body waves, and potentially the ground rotations that occur as a result of those complex wave fields. So there's a lot to be learned, both in the geophysics simulation, but also in the coupling to rigorous coupling to engineering simulations. And so this forum is really going to discuss the full breadth of numerical analysis approaches for looking at these problems. And we've asked each of the invited speakers to think about describing the progress that's been made, as well as identifying the remaining challenges. And so we hope that we can really illuminate, you know, sort of the cutting edge of where things are in this forum, as well as what remains to be done and what are the challenges to bring this into fruition as a practical tool. This is a really, really difficult problem. We're trying to model all the way from the fault rupture, propagation through the earth, propagation through soil, and then into the structural system. It's, first of all, obviously a multidisciplinary problem, and it resides at the nexus of earth science and engineering. And if you look at the forum today and tomorrow, you'll see there's a full multidisciplinary breadth of participants to cover those domains. It's really challenging multi-scale from a computational standpoint. We may have to model the Earth at ranges of 100 to 200 kilometers or even more, depending on the size of the earthquake. And yet, we want to generate ground motions that are representative at a scale of hundredths of a kilometer here for a particular structure. And so that really drives some significant computational challenges. For strong ground motion, we're generally going to be coupling at some level linear and nonlinear systems. Our building systems are going to be responding nonlinear during an earthquake, and certainly the potential for soil nonlinearity occurring. There's a lot of uncertainties in this problem parametrically, particularly for the subsurface, where our geologic understanding of our geologic realizations, you know, are challenged when we start to compute ground motions at very high frequencies. So we've got a session devoted, for example, to just looking at the techniques for improving our geologic understanding and how do we handle that uncertainty in the geologic structure. And then finally, you know, there are extreme computational demands associated with this problem. There's no way getting around that. It's just a problem that takes, you know, the cutting edge computational capabilities, as Khalid had mentioned, to begin to resolve and solve this problem. So why now? Why is it so compelling to have this discussion now? Well, you know, in our view, we're really at the precipice of a really dramatic advancement in capability here over the last few years and in the near future. And part of that is driven by the ever increasing computational capability that's occurring. And I'm showing a plot of the #1 ranked computer in the world by year here in this plot. And the vertical axis is a measure of floating point operations per second on a LIMPAC benchmark. One of the remarkable things you see for the last 20 years is this curve is continuously up and to the right. And so computational capabilities just continue to increase. Every time you think the computer science community has hit a ceiling with respect to the technology and the hardware, they get clever and figure out something new. And so we're moving towards GPU-based systems. And so we're really having this mega increase in computational capability, which is germane to this problem. Secondly, by the result of work that a lot of the research community is doing good work, and we hear about a lot of it in this workshop, we're really advancing the understanding of earthquake processes. Just for example, we're beginning to understand, to be able to quantify and characterize how a fault ruptures and the characteristics of the fault rupture. We have a whole session dedicated, the first session up, to fault rupture mechanics in characterizing that fault rupture. So we're making big strides both computationally and in terms of understanding the phenomenology. And that is really enabling, in my view and in the committee's view, the ability to do these types of calculations. So let me just speak briefly to how we've laid things out. If you've looked at the agenda, you'll see in day 1, we are touching on all the core elements of regional scale simulations, starting with the earthquake rupture source, moving through nonlinear structural and soil response. We've got a session dedicated to geologic models to support high frequency simulations. There's different ways to skin that cat using both deterministic and stochastic representations of geology. How do we represent near surface geotechnical layers? And in a lot of the early simulations that have been done, we've often neglected that vexing near surface geotechnical layer where there may be very, very low wave speeds, shear wave speeds, and nonlinear behavior. So how do we need to deal with that in the long term? How do we, I alluded to this, how do we couple our geophysics and engineering models? There's different modalities for doing that. There'll be a discussion about that. And then finally, we'll have a discussion of the computational considerations in terms of integrated workflow, performance, and computational demand. So day 1 is dedicated to all of the underlying technology one needs to do these types of simulations. Day 2, we shift gears and we begin to talk about how do we build confidence in these regional scale simulation tools so that they can transition from being a pure research activity to an actual broadly applied activity. And so we'll talk about metrics and acceptance criteria for synthetic motions. How do we decide whether a synthetic motion is useful or not? How do we characterize and propagate uncertainties that are going to inevitably be there in our models? And how do we do rigorous verification and validation of simulation results? A lot of discussion about that. The last 2 sessions will be how do we transition these things to practice for performance-based earthquake engineering? And we'll get some perspectives from folks that have thought a lot about this and what is the right phased approach for beginning to transition these into practice. And it's really time to be thinking about that strongly. And then finally, what operational, we'll have a panel discussion on what operational models could we foresee out there to broaden the community access to these technologies and actually begin to move these simulation capabilities from an R&D environment in the community application. And so we've got a jam-packed agenda that goes all the way from technology development to brainstorming, if you will, about how to transition this into practice. So we're really, really excited about the content of this forum, and we really are pleased that we got such a great attendance, as Khalid mentioned. And so I am going to now turn it over to Amarnath to talk a little bit about the mechanics of how the forum is going to actually operate.